students, let's do another example of short circuit analysis. Basically, this is three-phase short circuit analysis. I am reading out the question. It says a single line diagram of a three-phase, three-bus power system is shown in figure. All the impedances are expressed as per unit on 100 amperes. The generators are running at the rated voltage. Determine the fault current, bus voltage, and the line currents when a fault with an impedance of 0.16 per unit occurs at bus 3. Let me first draw the figure and then I will repeat the question. Right? So this is that we have a generator with an reactance of J 0.1. Right? After that we have a transformer with a reactance of J 0.1 again. This is coming to bus number 1. Bus 1 and bus 2 are linked with the reactance of J 0.8. Right? Then we have another generator with the reactance of J 0.2 and then another transformer with the reactance of J 0.2. Now what the question is saying that we need to find out this is basically question number 3. It's already given that base MVA equals to 100 MVA, base power equals to 100 MVA, and we need to find the short circuit current, voltages in case of short circuit, V2 SC equals to this, V3 SC equals to this. And here the difference is that we are given a fault impedance of 0.16 fault impedance, right? And the fault is at this point. So basically this is ZF equals to 0.16 J, and this fault has occurred at bus 3. So now since this system is already modeled on a common base, so there is no need to change the base, and the fault we are talking about is a symmetrical fault. Always remember that the fault is a symmetrical fault, and for this fault we need to find the fault currents, bus voltages, and the line currents as well. And we also need to find the line currents as well. Okay? This is a symmetrical fault. That is a three-phase fault, which we also call as the balanced fault. So the very first thing that we need to do is to remember the formula. We know that I3, that is the fault current in case of bus 3, or we can say that ISC for bus 3 is equals V divided by XF times 100, and since we have per unit here, so it would be the voltage in per unit divided by the reactance in per unit, right? So multiplied by 100 divided by 100, so 100 is cancelled out, right? Previously we were putting the reactance in percentage, and that is why there was a 100 here, because and since here in this scenario both the values are in per unit, since the generator voltages are not mentioned here, so but it is mentioned that the generators are operating at the rated power, so it would be 1.0 rated voltage, sorry, 1.0 divided by XF plus ZF. XF is the fault reactance and ZF is the fault, XF is the Thevenin reactance plus ZF is the fault reactance, right? Let's name this equation as equation 1. Now, the equivalent Thevenin circuit, let's draw this circuit. So, this would be equivalent circuit. So what will be the circuit now in this case? We have two generators, both of them will be grounded. Then we have two transformers as well. So this is xg1, xt1, xg2, xt2, and then we have this x, let's name them, right? We have this one as xg1, xt1, xg2, xt2, let's name it as x12, x23, x13, right? So x12, and then we have x23, x13, and finally we have this ZF, right? Now here you can see that this circuit is a bit complex. Why? Because these impedances can be simplified, but after one step we need to solve out the star delta interconnection. First we can see that these two reactances and these two, they are in series, so let's solve them out, right? So this will be, let's name them as xgt1. xgt1, this means generator plus transformer, and xgt2. So now our equivalent circuit will look like this. ZF or XF, right? And this will be ground. So let's name it as xgt1, xgt2, then we have x12, x13, and x23, right? And now you can see that we can no more simplify the circuit, but what we can do is we need to convert this circuit from delta to star or star to delta, or we can have multiple methods. What I am doing here is I am converting this delta of x12, x23 and x13 into its equivalent star. We know that how in star delta interconversion is performed, that whenever we are converting a delta circuit, so what is the characteristic of delta circuit? These are end-to-end connected, 1 end, 2 end, and 3 third end, no common point exists. So whenever we are converting it into a star circuit, the first thing that we need to do is we need to define a common point, right? So let's name them as XA, XB and XC. And then how will we carry out this star delta interconversion? So now XA, how will we find XA? This is XA, right? The denominator is same. This is X12, sum of all the three delta resistances, X23 plus X31, and for numerator it is the product of the two delta resistances through which this XA is directly connected. This means X12 and X13. So we find out this value to be 0.2 J per unit. Similarly, we can find XB. XB is this one. This will be the product of X12 times X23 divided by X12 plus X23 plus X13, and this will be equal to 0.2 J per unit again, and XC will be equal to 0.1 J, and all these three will be in per unit. So now when we simplify this circuit, it will look like this. Let's draw it again, the simplified version. This is XGT1, XGT2, ZF, or we can also call it as XF, right? So now the percentage XF, we can calculate that percent of XF. We can see this branch is in series, this one is also in series, and these two will be in parallel, and this one is again in series. So the equivalent reactance in this scenario will be these two are in series, so equivalent will be 0.4 J per unit, 0.6 J per unit, and again these two in series, 0.2 J per unit. So the equivalent will be 0.4 parallel to 0.6 plus 0.2 J, right? So we can solve it. 0.4 J times 0.6 J divided by 0.4 J plus 0.6 J plus 0.2 J. This would be 0.34 G, right? Just a minute. In fact, it would be 0.5 G, right? I have included the fault reactance also there, right? So now the formula will be ISC in case of fault at bus 3 equals V divided by percentage of XF. Yeah. If I had not included this ZF, then it would be plus ZF, but here I have already included this ZF, so it's already a part of this XF. So it would be 1.0 divided by 0.5J. So ISC3 is equals to what? Minus J2 per unit. Now what does this minus J2 sign indicates? It indicates the inductive current. because we know that the current in an inductor lacks the voltage. So we have found out the value of current. If we are given the base, we are already given the base power. If we are also given the value of base voltage, then we can find out the base current, and we can find out this value in kiloamperes, right? So now the next thing we need to find is the voltages. So how can we find the voltages? The V3, V2 and V1. So the first voltage is V3 of F, that is V3 in case of fault, right? So what will be this? This would be I3 times ZF. So I3, by I3 we mean I3 short circuit. This is simply Ohm's law. So this would be minus J2 times J 0.16, and the voltage is 0.32 per unit. And always remember, this is only possible because this was an unbolted fault. If it would have been a bolted fault, then V3, that is the voltage at the bus where the fault has occurred, would have been 0, right? Since this was an unbolted fault, that is why the voltage is non-zero, but still you can see that the voltage is pretty low. Now we already know V3, but we need to find the values of V1 and V2 and also the line currents. Coming back to the original question here, you can see this is actually V3. So we have already found out the value of V3, this which was I times the fault impedance, right? Now we need to find out the value of V1 and V2. For this we need to check out the currents as well, right? We know the total current. The total fault current we have already calculated it at this step. Is that IF is ISC3 basically is this fault current which is flowing through this path, or which is coming towards the three-phase fault, right, at this point. Now this fault current will be supplied from either of the sources. This is understood. Either this fault current will be flowing from this generator, generator 1, through transformer 1 to the fault point, or this fault current will be flowing from generator 2 through transformer 2 up to the fault, right? So what we can do is we can find out the currents in both of these branches, and once we know the currents at both of these branches, we know the generator terminal voltage. Here we can find out the generator terminal voltage as well as the terminal voltage at the transformer end as well, right? So now let's apply CDI. We know the total current, the fault current is what? Minus 2J. So using CDR, that is current divider rule, the current from generator 1 in case of fault will be equal to what? The opposite impedance. This is generator 1 path we are talking about. So in numerator we will have the opposite impedance, which is 0.6J, 0.6J divided by the total impedance 0.6J plus 0.4J, 6J plus 0.4J times the total current, which is ISC3, right? So this when simplified gives us as minus J 1.2 per unit. This is the contribution from generator 1, and since we have only two generators, so we know that the contribution from generator 2 in case of fault will be what? The total current minus the contribution of generator 1, and this is equals to 0 point minus j 0.8 per unit, right? So I hope that it is somewhat clear now. It will further become clear. So let us come back for a moment to the original question. We have found out the contribution from each of the generators. So this generator current, we have already found out that okay, Ig1 in case of fault. What we have also considered is that the terminal voltage of this generator was 1 per unit. This means that this generator is operating under rated voltage. We already discussed that. So now the voltage at this point is 1 per unit, and we need to find out the bus voltage at bus 1, the voltage at bus 1. So this would be how much? 1 minus the voltage drop across the transformer. Getting it? So this would be 1 minus the voltage drop across the transformer. Clear? So we need to consider two voltages here. The first one is the voltage drop across this generator resistance, and the second one is the voltage drop across this generator reactance, transformer reactance. The generator reactance and the transformer reactance. Or if you look at the simplified circuit, basically we are talking about the voltage drop at this point. The generator at this point operating at 1 per unit, and we are talking about this is bus 1. So whatever drop has occurred across xgt, we need to subtract it, and this is my point here, that the generator is operating at this level 1 per unit. This is 1 per unit. There will be a drop across the generator reactance, and there will be a drop across generator transformer reactance. Basically 1 per unit is the generator internally generated voltage. I am sorry, I think in the previous sentence I said it's terminal voltage. The terminal voltage is at this point, which is not 1 unit. The internally generated voltage for both the generators is 1 per unit, and then there is some drop at the generator reactance as well as the transformer reactance, and after this drop we have what? V1 and V2, right? So now the value of V1 would be how much? V1 equals to 1. Why 1? Because the generator internally generated voltage is 1 minus xgt1 times Ig1 in case of fault. So this is 1 minus j0.2 times minus j1.2. This is Ig1, this is j0.2, we have already calculated, and this will give us 0.76 per unit. This is V1, right? Next we have to calculate V2, this will be calculated in a similar manner, 1 per unit minus j0.4, which is xgt2 times minus j0.8, which is Igt2. We have already calculated it in the previous slide. Just let me refer it. This is Ig1, this is Ig2, and this is xgt1, this is xgt2. Right. Coming back here, so V2 in case of fault will be equals how much? 0.68 per unit. So we are now done with all the three voltages, V1, V2 and V3. The only thing that we need to that is remaining is the line currents. Line currents means what? How much current is flowing through line 1, 2, how much is flowing through line 3, 1, 3 and line 2, 1. For that we need to again refer to the main SLD. These are the line currents, that how much current this line is carrying, this line is carrying, and this line is carrying. So between 1 and 2, from 1 to 3, from 2 to 3, and from 1 to 2, right? How can we find this? Again, using Ohm's law, we know that the current travels as the difference of voltages. So as a last step, this one is, so calculating line currents, we know I12 in case of this fault will be equal to V1 in case of fault minus V2 in case of fault divided by Z12 or X12 as we are. So this will give us minus J 0.1 per unit. Similarly, I13 will be equals to V1 minus V3 divided by Z13. This will be minus J 1.1 per unit, and I23 in case of fault will be equal to V2 minus V3 divided by V23 equals to minus per unit. So this ends our question here, right? These three values were required. These are the required line currents. And again, if we have the value of base voltage, we already have the base power. Let's say we have base voltage, whatever it is. Let's say like V base is equals to 11 kV. Then what we can do is calculate the base value of current on either side of the transformer. For that, we need to also know the generation of transformer ratio. Like transformer ratio is, let's say we have the transformers as 11 kV by 0.4 volts. Then we can find the base current on either side of the transformer, like on this side as well and on this side as well. And based on which side we have the fault, we can find out the base value and multiply the per unit current with the base current to find out the positional value, right? Let's say we have the value, of course, on the at the secondary end of the transformer. So what will be the base current? I base equals to S base, which is 100 MVA, divided by under root 3 of V base, right? So this will be 100 exponent 10 to the power 6 divided by under root 3 times V base is 0.4 kV, or we can say 400 volts, right? So I base will be equal to how much? 100 divided by would be 144 kiloamperes. Just let me recheck the calculations. Okay, so this value of current is a sort of unrealistic because we do not have like circuit breakers of 300 kiloamperes. So in order to just make it more realistic, I am considering the voltage ratio as 11 kV by 6.6 kV. So this will give me the value of current as 8.75 kilo amperes, right? And my actual value of I3F would be how much? The I3F in per unit multiplied by I base on the bus 3 side. So this would be 8.75 times my current was how much? -2, right? The fault current was -2, yeah. So its magnitude would be 17.5. I3F magnitude would be 17.35 kiloamperes. So whatever I am equipment, breakers or bus bars I am using at the bus 3 side, they should be able to bear this 17.5 kiloamperes. If their short time rating is lesser than 17.5 kiloamperes, then that equipment will burn out. It is not recommended for use at bus 3. Similarly, when we are carrying out design of the system, we need to calculate the voltage, the short circuit current at bus 1 also, at bus 2 also, and accordingly we need to select the equipment breakers. So let's go through this question again for a quick review. So the first thing that we have done here is we were given a question. I am reading out the statement again. It says the single line diagram of a 3-phase power system is shown in figure. All the impedances are expressed in per unit on a 100 MVA base. The generators are operating at the rated voltage and determine the fault currents, bus voltages and the line currents during a fault when a fault impedance of J0.16 occurs and a fault with impedance of J0.16 occurs at bus number 3. So the very first thing that we checked in the system is that all the impedances were already marked with respect to a common base, and we were asked to calculate the short circuit current, the voltages, bus voltages in case of short circuit, given that AS was an unbolted fault. So we checked out the system. Generator and transformers were in series. We added their impedances together. Then we added the line. Then we included the line impedances and saw that it was forming a delta connection. We converted this delta connection into its equivalent Y connection, and then we said that we can solve these equations as a combination of series and parallel. So we find out the short circuit current at -J per unit. So this was the short circuit current, and if we have the value of the base impedance like we had here, this from this red color, we can find out the actual value of short circuit as well. Next we calculated the contribution of each the bus voltage I times GF, since this was an unbolted fault, so the voltage at bus 3 was non-zero. Even if it is a bolted fault, the voltage at bus 3 will be 0, but the voltages at bus 1 and 2 will be non-zero. When we used CDR, we found out the contribution of each generator, and then we found out the value of voltage at each bus, because it was given that the voltage is 1 per unit, right? So we calculated the line currents, and then we assumed that this base voltage is 11 kV and a transformer 11 kV at generator side, and the transformers are stepped down with a ratio of 11 kV by 6.6 kV. So we calculated the base current at the 6.6 kV side as 8.75 kiloamperes, and we found out that this I3 is 17.5 kiloamperes, and the line current flowing through I12, line current flowing through I12 will be how much? The line current flowing through I12 will be 0.875 kiloamperes. This one will be I13 will be 8.75 times 1.1. The magnitude I am only talking about, this will be 9.625 kiloamperes, and I23 will be 0.9 times 8.75. So this would be 7.875 kiloamperes. And now we can also convert the bus voltages these buses 1, 2 as well as 3 were all after the transformer. This means their base voltage is 6.6. So 0.76 times 6.6, so the base voltage is 5.016 kV at bus 1. At bus 2 it is 4.488 kV, and at bus 3 this would be, it's there. So at bus 3 the base voltage would be 0.32 times 6.6, so this is 2.112 kV. So this was all about a detailed example of three-phase short circuit analysis, which we also call as symmetrical short circuit.